Hello friends, in previous video we have seen about the various theoretical aspects of coupling, classification and various functions of coupling. Now in this video we are going to start the design procedure of flange coupling. Let's start. So flange coupling consists of two cast iron flanges each mounted on each shaft, end and keyed to it. Please see what it is written here. Flange coupling consists of two cast iron flanges each mounted on each shaft, end and keyed to it. The second one is the faces of couplings are turned up to right angles to the axis of shaft. See guys, what it is written here. The faces of couplings are turned up to right angles to the axis of the shaft. Second one is then one of the flanges has projected portion and one having recessed. Okay, one of the flange has projected portion and one having recessed. Then this helps to bring the shaft in line and to maintain alignment. Okay, because of this projected portion, it helps the shaft to maintain in line and to maintain alignment. Then two flanges are coupled together by means of bolts and nuts. See guys, there are two different flanges which is made up of cast irons that we have seen earlier. That two flanges are coupled together by means of bolts and nut in flange coupling. The next one is they are generally used for heavy loads and in permanent installation. See guys, flange coupling, rigid flange couplings are used for heavy loads and in permanent installations. The next is they have the advantage of being shorter and lighter than any other heavy duty coupling. See guys, what advantages flange coupling has? They have the advantage of being shorter and lighter than any other heavy duty coupling. Okay, it means that the coupling which is used to carry heavy duty heavy load, or the coupling which is used under heavy duty operations, so flange coupling has the advantage that it is shorter and lighter as compared to them. Okay, so this is about the introduction of flange coupling. Now let's see what it is. Now the heading that we are seeing is types of flange coupling. Now what are the various types of flange couplings are? Please see. One is unprotected type, second one is protected type, and third one is marine type. These are the three basic types of flange coupling, that is unprotected type, protected type and marine type. So let's see with the unprotected flange coupling design procedure. That diagram that we are seeing is the unprotected type flange coupling, and you can see there are two different flanges as we have seen in the theoretical portion. You can see this left one and this right one. These flanges are made up of cast iron. You can see this flange. Okay, this hatching line shows flange part. That is, this is left one and this is right one. These two flanges are made up of cast irons. This is hub and this is shaft. You can see this is shaft. So this coupling is used to connect two rotating shaft. Okay, this is flange coupling. So it is a type of rigid coupling. So it means the shafts are in perfectly aligned. That is why we are using flange coupling to connect them. Okay, then there are various dimensions that we are seeing. This is the key which is used to connect this hub to the shaft and flanges. And again these are various dimensions. You can see that is d is equals to twice d, then d1 is equals to thrice d, and d2 is equals to 4d. So what it is actually we are going to see in next slide, that there are various notations regarding flange coupling that we are going to see. Now notations. Now see guys, these are the notations. On that notations, please see what it is written here. Small d denotes diameter of the shafts. Okay, small d denotes diameter of the shafts. Capital D denotes outside diameter of hub. D1 denotes pitch circle diameter. Capital D2 denotes outer diameter of the flange. Capital L denotes length of the flange. TF, small tf denotes thickness of the flange. Then capital DC denotes core diameter of the bolt. Capital DO denotes outer diameter of the bolt. Capital N denotes number of bolts. Small t denotes thickness of the key. Small w denotes width of the key. And small l denotes length of the key. So these are all the notations which we are using in designing of flange coupling. Okay, now without wasting time, we just starting the step 1 for designing of flange coupling. Please see what step 1 tells us. To find torque acting on the shaft. See guys, step number 1 is to find the torque acting on the shaft. While designing flange coupling, the first step is to find out the torque which is going to act on the shaft. So the formula for torque is T is equals to 60p divided by 2 pi n into 10 raised to 3. So this formula is nothing but the power formula, that is P is equals to 2 pi nt by 60. From that formula we have manipulated this one and we have written in this form. So using this formula, the torque T acting on the shaft is calculated. So this is the step number 1 for flange coupling. Step number 2 is to find diameter of shaft to transmit required torque. See guys, to find diameter of shaft to transmit required torque. So T is equals to pi by 16 into tau into d cube. So this center term, that is which is called as tau, okay, which is indicated shear stress. Okay, so pi by 16 into tau into d cube. So by this relation you can easily calculate the diameter of shaft, which is denoted by small d, because we have value of T in previous step, that is in step number 1 we have calculated the value of torque, and we have pi by 16 value and tau value which is given to us in numerical. So we are left with the diameter of shaft, that is small d. So we can easily find out the diameter of shaft by this relation. Now step number 3 has some more sub stages. Please see, step number 3 has design of flanges. Step number 3 is design of flanges. So step number 3A, okay, so first stage of step number 3, that is A, what it is tells us, please see, empirical relations. Okay, so in step number 3rd of design of flange, we need to fix some standard empirical relation. We need to fix some dimensions by using some standard empirical relations. And what are these empirical relations? Please see, capital D is equals to 2 into D, that is twice of small d. Capital D1 is equal to thrice of small d, and capital D2 is equal to 4 times of d. Then small l is equals to 1.5 into d, TF is equals to 0.5 into d, and TP or is equals to 0.25 into d. So these empirical relations we have observed in our diagram also. Okay, so step number 3A tells us to fix some standard dimension by using empirical relations. Next is step number 3B. See guys, what it is tells us. Step number 3B is design of flanges. Please see, design of flanges. So step number 3B step is check shear stress in hub. Okay, check shear stress in hub. Now see, for that T is equals to pi by 16 into tau. I am repeatedly telling you this symbol is for tau, which shows shear stress. Okay, and we are checking the shear stress in hub. So T is equals to pi by 16 into tau into d cube of 1 minus k raised to power 4. Now what do you mean by k is, please see, where k is equals to d by d, small d upon capital D. To calculate the value of k, we need to divide this diameter of shaft with the diameter, okay, capital diameter. So d taken as twice of d, capital D is taken as twice of small d, so d is equals to 2d as per empirical relations. Okay, also length of hub is equals to 1.5 times d, that we need to take. So we, by this step, our induced stress, that is twice equals to induced shear stress, we can find the induced shear stress, and our induced shear stress should be less than allowable shear stress. Okay, induced. So by this relation, by using this relation, we need to calculate the value of this tau, and whatever will be the value for this tau that we have calculated will be the induced shear stress value. Okay, the stress which is induced during a phenomena operation, that is the induced shear stress, and that according to safe design condition, induced shear stress should be less than allowable shear stress. Okay, allowable shear stress value is given to the numerical. Okay, then next is step number 3C is check shear stress in the flange. Please see guys, in previous step we have checked shear stress in the hub, now we are checking shear stress in the flange. So force is equals to area resisting stress, therefore T upon capital D upon 2 is equals to pi into D into TF into tau. This is tau. So find induced stress. So we have in this step also we need to find out induced stress tau, which is for flanges, and for safe design condition, induced shear stress should be less than allowable shear stress. Okay, now we are on this step number 4. So step number 4 tells us design of key. See guys, we are designing key which is used to hold two flanges and shafts. Okay, empirical relation. So tells us some empirical relations. So what are these? Please see, W is equals to T, that is width is equals to thickness is equals to D by 4. When we need to take T is equals to D by 4 or W is equals to D by 4, if crushing stress is twice the shear stress. Please focus your attention over here. If the crushing stress is twice the shear stress, then we need to take W is equals to T. Then W is equals to D by 4 and T is equals to D by 6. See guys, W is equals to D by 4 and T is equals to D by 6. We need to take it when if crushing stress is not twice the shear stress. If your crushing stress is not twice the shear stress, then we need to take W is equals to D upon 4 and T is equals to D upon 6. And length of key is equals to length of flange. Your length of key must be taken is equals to length of flange. Then step number B is check shear stress induced in the key. So what is the formula? T upon D by 2 is equals to W into L into tau. So we need to calculate the tau, which is induced shear stress, and for safe design condition our induced shear stress should be less than allowable shear stress. Then next is step number 4, that is design of key. See guys, design of step number 4C is check crushing stress induced in the key. Key is subjected to crushing failure, that is why we need to check the key for crushing stress. So what is the relation for that? T is upon D upon 2, T upon D by 2 is equals to T by 2 into L into sigma C. So we need to find this induced crushing stress, that is sigma C, and that induced crushing stress should be less than allowable crushing stress for safe design condition. Okay, this is our step number 5, that is now design of bolts. So step number 5th A is number of bolts. So small n is equals to 4 if diameter of shaft is up to D less than 55 mm. Take n is equals to 6 if diameter is between 55 to 150 mm. And take n is equals to 8 if diameter is above D is equal to 150 mm. Then B is equals to shear failure of bolts. See guys, shear failure of bolts means what? T upon D1 by 2 is equals to n into pi by 4 into DC square into tau. So DC will be determined by this relation. DC will be determined and DO is equals to DC upon 0.84. The bolt size should be rounded to nearest even number. See guys, the bolt size should be rounded to nearest even number. Okay, and these are all the steps of design procedure of your flange coupling. Thank you.